Okay, this is the first lesson which we're running on gravity, one of about 3 or 4. Now this is all based around Newton's great ideas. And Newton came up with an equation that said, we're going to start from this point, the force is proportional to the product between the two masses divided by the separation squared. Of course, I hope you know that gravity acts between two masses, and if one is larger, there's a greater force of gravity. It's the product of these two masses that creates the force of gravity, and it's also measured from the centre. The separation is measured from the centre of those two masses. Okay, so if you ever to write an equation for it or to write an answer, it's going to be the force is proportional. Now let's write this out. So the force is proportional to the product of the masses and inversely proportional to the separation squared. Good, right, so with that in mind, what do we need to talk about next? We need to talk about this minus sign implies that it's an attractive force, and I'll explain a bit more of that. Attractive force. I'll explain a bit more about that in one of the later videos. And this G here, or we call it big G, is the gravitational field constant. Okay. And big G is given the number 6.67 times 10 to the minus 11. If we need to work out the unit that, we can do a dimensional analysis. However, meters per kilogram per second squared. Excellent. So that's, I mean, it looks quite a simple equation on the face of it, but it has a lot of implications. So we're going to run through a few examples. Here's the first one. Let's imagine there's me standing on the Earth, and the radius of the Earth we know is 6,400 kilometers. And I want to know how much force I'm being pulled down to the Earth with if I'm at a separation of 6,400 kilometers, and also knowing that the Earth, the mass of the Earth, is 6 times 10 to the 24 kilograms. So given that detail, what do you think the force pulling me down is? If you think you know, you can hit pause. Otherwise, watch this solution. So we simply write out the equation. F equals G. We can forget about the minus sign in the first instance. We're just looking for magnitudes. So let's plug in the numbers and see what we come up with. 10 to the minus 11 by... And I didn't tell you what mass I was, but let's just assume that my mass is, just because it's a round number, about 100 kilograms. It's by 100. And divide that by the separation squared, 6400. Careful, it's in kilometers, and then we square it up as well, giving me something in the order of 977 newtons. So that's the force in which I'm being pulled down to the Earth with. Interestingly, as well, because forces exist between two objects, just like we said in the beginning, there is an equal and opposite force pulling on the Earth upward by myself, because these forces must be working in a pair. That force is simply 977 newtons being pulled up. Okay, now let's think about what would happen if it were just 1 kilogram. 1 kilogram sitting at all the same distances, 6400 kilometers, and the mass of the Earth again is 6 times 10 to the 24 kilograms. Okay, what force is exerted there? We write the equation down again, and this time 10 to the minus 11 by 6 times 10 to the 24 by 1 kilogram. Divide that by, being careful about the kilometre conversions, and making sure you square it, turns to 9.77 newtons. 9.77 newtons for 1 kilogram. So we could say it's 9.77 newtons per kilogram. And does that ring any bells? Well, 9.81 newtons per kilogram is what G is on Earth. So really, G, big G, all the way up here, and little g are related via Newton's law of universal gravitation. And the way that we link it is just merely saying that the force divided by the mass is an acceleration, which in turn is g, which is g m m over r squared, which is the force divided by m, which gives us g is gm over r squared. So that is how you link big and small g. This, of course, is the mass of the Earth. Good, so let's try another one. Let's try this time, what's the force between very massive objects? Needless to say here, of course, that this, being such a small value, must mean that the masses are huge in order for the force to even exist. So gravity only acts when you have very, very massive objects. Let's try one more. Let's see if you can solve this one. Two brass or iron balls, very heavy. They are 50 centimetres in diameter. That's meant to be a 50, and they are 5 times 10 to the 3 kilograms each. The separation of their centres is 2 metres. So the question is, what is the force that exists between them? If you think you know, hit pause and give it a go, otherwise here comes the solution. Okay, just to be absolutely pedantic, we need to write this out all the time, and because this time the masses are the same, we can just say gm squared over r squared, which might make life a little easier for us. So here we go with the substitutions. 5 times 10 to the 3, let's square that up and divide it by only 2 metres squared. And that gives us something like 4.2 times 10 to the minus 4 newtons. So a tiny force. Negligible, even though this is half a ton. No, sorry, that's a... Goodness me, that's incredibly heavy. That is 5,000 kilos, that's 5 tons, that's 5 tons. It's still a very small force. Okay, let's move to another example. What about the Earth and the Moon in that case? We know the mass of the Earth, of course. Let's write that down again. It's going to be 6 times 10 to the 24 kilograms. The mass of the Moon this time is smaller, considerably smaller, though it doesn't look it, only 10 to the 22, though that 10 to the 22 is 100 times smaller. And their separation of their centres, 3.6 times 10 to the 5 kilometres. Now, often big distances will be given in kilometres. Watch out, because actually we need to use it in metres. So what's the force that exists between the two? Well, if you think you know, hit pause. Otherwise, here we go. F is minus gm m over r squared. But we'll be pedantic, we'll write it all in. 6.67 10 to the minus 11 by 6 times 10 to the 24 of the Earth by 7.3 times 10 to the 22, because remember, you need 2 masses for the force to act between, and divide that by 3.6 times 10 to the 5 times 10 to the 3 in kilometres, square that up. It gives us, something in order of 2.3 times 10 to the 20 newtons. Quite significant. However, of course, that's keeping the Moon in orbit around the Earth, so you might think it should be bigger than that. Right, well, I'm sure you can imagine how this and the ideas of circular motion come together. Let me just remind us of ideas of circular motion. Because for all celestial bodies, which are as good as circular motion, they're going round, the force of gravity provides the force required for circular motion. So you will have the Earth and the Moon moving at a velocity with a force acting at right angles to the motion, so not changing the velocity, the speed, but changing the direction, hence changing the velocity. And the equation, of course, for circular motion, the force required for something to go around in a circle is the mass of that object, mass of the moon, the velocity of the object squared, and the separation between the two of them. The force of gravity provided is gmm over r squared. So if these are equal, then the object will go around in circular motion. So, I suppose we could say to ourselves, first of all, how fast does the moon move round the Earth? What is its velocity? So we're first of all going to work out its velocity. And then from that we're going to work out the time period. And we're going to see if the time period correlates with what we know the time period, the one rotation of the moon, will be. So let me keep those question marks hanging around there, because if you think you know how to do it, you go for it. There are a few steps in the way here which are unfamiliar to you, but not that which you can't work out. Okay, here comes the answer. So let me rewrite that all over again. mv squared over r. It's gmm over r squared. I'm not worried about the minus, it's a magnitude question. The m's disappear, the r's disappear, leaving us with v squared is gm over r. Or indeed, the velocity is going to be the root gm over r. And the mass that dropped out, of course, was the mass of the moon, because the mass of the moon is small m. Big M left is the mass of the Earth. So the speed, of course, is going to be 6.6. Well, let's substitute. Minus 11 by 6 times 10 to the 24. Divide that by the separation, which was 3.2 times 10 to the 7 meters, and square root the whole thing. And that should give us, not to the 7, 3.7 times 10 to the 8, apologies. And that should give us a velocity of about 1,054 meters per second. Okay, so the next question is, what is the time period? Well, knowing this is going around in a circle around the Earth, and we know the separation, which is r, we can say that the circumference of that circle in which it draws out, divided by the velocity, will give us the time period, the time it takes to go around the Earth once. So 2 pi by 3.7 10 to the 8 over 1054 meters per second, and that gives us 2.15 times 10 to the 6 seconds. What does that equal if we divide it through by the number of seconds in a minute, the number of seconds in an hour, and the number of hours in a day? And that gives us 25 days, which is approximately 1 month. So hopefully that makes sense. And the moon does take about a month to go around the Earth. Good. Okay, then let's look at another example. Let's imagine that we have the Sun, and this is the Earth. And the Earth is going around the Sun at a separation of, I mean, it's not drawn to scale, of course, but 1.5 times 10 to the 11 meters. We know the mass of the Earth is 6 times 10 to the 24. The velocity is going to be the circumference divided by the time period, and we know the time period because that is 1 year, which is 3.2 times 10 to the 7 seconds. That's a good one to remember, by the way. So can we find the mass of the Sun knowing all that data? If you think you know, hit pause. Otherwise, here comes the answer. Okay, mv squared over r is gmm over r squared. This is the mass of the Earth, the Sun, the Earth, so that drops out. The separation, let's drop that out. And therefore that leaves us with v squared is g mass of the Sun over r. Going back, mass of the Sun is going to be v squared r over g. Now, we know that the velocity is going to be 2 pi r over t. That gives us 2 pi r over t squared by r over big G. Okay, let's bolt in the numbers. 2 pi by 1.5 times 10 to the 11 over 3.2 times 10 to the 7 squared up by 1.5 times 10 to the 11 divided by 6.67 times 10 to the minus 11. Oh, that's quite convenient, isn't it? And the answer it gives us is a grand total of 1.95 times 10 to the 30 kilograms. That is the mass of the Sun. So what's that? That's if we were to the 24, that's a million times larger than Earth. Which I think makes sense. Another example, you see how useful this is. Another 2 examples. Okay, Earth and the International Space Station. It flies around with a time period of 90 minutes. If it's going around at 90 minutes, what is the radius of its orbit from the centre of the Earth? Okay, bearing in mind all the previous data, if you think you know, hit pause, otherwise here comes the answer. Good, so the equation for circular motion and the gravity that's providing the force for circular motion, let's just get rid of those. Gives us that v squared is gm over r. And of course the velocity is the circumference, we've done this before, divided the time period squared. So, now slightly harder rearrangement here. We are looking for, so gm, let's hold that up there. We're going to take the 2 pi squared down below, so it becomes 4 pi squared because I've squared it. And I'm taking t squared up, leaving me with r squared multiplied by r cubed. Therefore, r is going to be the cube root of 6.67, 10 to the minus 11, by the mass of the Earth, 6 times 10 to the 24, by the time period, which is 90 minutes, convert it into seconds, square it up, over 4 pi squared, rooted, gives us a grand total of 9.7 times 10 to the 6 meters. Good, okay then. And then, what are we going to next try? Okay, what about a geostationary satellite? And I'm sure you know the geostationary satellite means that as the Earth rotates, this geostationary satellite stays above the Earth at the same time, so it must have the same omega. Good. So let's try this then. So, mv squared over r, as we've started all the other ones, is gmm over r squared. We could also write v as omega r, so the whole of this is m omega squared r. And we're looking for the radius. Take out the m's. Gm over r cubed square rooted gives us r. Omega, sorry, gives us omega. And we're looking for the distance, we're looking for r. So, sorry, slight rearrangement there. So we're going to go gm over omega squared, cube rooted gives us r. Good, so what is that? 6.67 times 10 to the minus 11 by the mass of the Earth divided by, what is omega? Well, it's 2 pi divided by the time it takes for 1 day, because this is geostationary, so that's 24 hours by 60 by 60. Make sure we square it, make sure we cube root it, and that gives us about 4.2 times 10 to the 7 meters. Actually, it's a long way out. Good. Okay, nearly there for uses. Just one last one, and that would be this concept of gravity. It can often confuse, because if you have something like the Jupiter, which is huge compared to the Earth, then we know that if you're standing on the surface of Jupiter, you're going to feel a very big force. Comparatively, when you're standing on the surface of the Earth, you're going to feel a smaller force. Okay? However, GMM, assuming you're the same person, over r squared, you have a bigger separation from the centre of the force on Jupiter versus the force on Earth. You've got a bigger separation on Jupiter than you do on Earth. So therefore, surely it should be this way around. Surely you should feel less force on Jupiter than you do on Earth. But no, that can't be true. This is true. And the reason why is because we are failing to see that though the radius increases, so the mass increases too. In actual fact, the mass is the density times the volume, which is spherical planets 403 pi cubed. So if we type that back into the equation for big M, that becomes density 4/3 pi r cubed M divided by r squared, mass of me. This goes with that, which leaves us with one single r. So the actual force is proportional. So the force is actually proportional to the radius of the planet that you're expecting. Something to bear in mind. Out of interest, what do we think the density of the Earth is? The average density of the Earth? Well, it's going to be the mass divided by the volume, which gives us 6 times 10 to the 24, divided by 4/3 pi 64,000 kilometers cubed. And that gives us 5461 kilogram meters cubed. Okay, I hope that really brings together what in essence is a very simple rule, but which has great consequences in stellar motion. I strongly advise you to learn this. Don't reach for a data sheet. I strongly advise you to learn that one. And it might be worth working out the number of seconds in a year. Okay, hope that makes sense.